Welcome to our fourth lecture in the second week of our course, Analysis of a Complex Kind. Today I'm going to show you how to find and plot and graph Julia sets. Recall that we're looking at polynomials of the form f of z equals z squared plus c, where c is a constant in the complex plane. And we're trying to find the locus of chaotic behavior. Those are all those z's in the complex plane that under iteration kind of behave chaotically. So where the iterates don't stay together. The Julia set we found is the boundary of A of infinity. And A of infinity was that basin of attraction to infinity. All those points z in the complex plane that go off to infinity under iteration of the function. So how do you find A of infinity and therefore its boundary, the Julia set? Let's start by finding the opposite of A of infinity, namely all those z for which the orbit stays bounded under iteration. So all those z's, so you can apply f as many times as you want to, but they never run off to infinity. That's called the filled-in Julia set. Let's look at some examples. F of z equals z squared. We looked at this function during the last lecture. This is the case where c is equal to 0, and we found that the Julia set is the circle of radius 1. Now we also know that points outside of that circle go off to infinity under iteration, and inside the unit circle are attracted to 0 under iteration. So all points on the circle and inside the circle do not go off to infinity under iteration, remain bounded in fact under iteration, and therefore form the filled-in Julia set for the function f of z equals z squared. We also looked at the function f of z equals z squared minus 2. So this is the case where the constant c equals minus 2. And we found that the Julia set is the interval from minus 2 to 2. And we also found that all points outside of that interval get attracted to infinity, so belong to A of infinity. So the filled-in Julia set is the same as the Julia set, namely the interval from minus 2 to 2 in this case. Let's look at another example. F of z equals z squared minus 1. So the case where the constant c equals minus 1. What is the filled-in Julia set in that case? Let's go find out. Again, we're looking at f of z equals z squared minus 1. So that's the case where this constant c is equal to minus 1. We want to find the filled-in Julia set. So all those points z that remain bounded under iteration. So let's check some orbits to get a feeling. For example, when z is equal to 0, then f of z is 0 squared minus 1, so that's minus 1. What's f of z? Well, f of 0 is f of minus 1, because we already calculated that f of 0 is minus 1. So we just need to apply f to minus 1. What's f of minus 1? That's minus 1 squared, which is 1 minus 1, so 0. If we apply another f to that, we get f of 0, which is minus 1. If we apply another f, we get f4 of 0, which is 0. And so the orbit just bounces back and forth between 0 and minus 1. 0 gets mapped to minus 1 under f. Minus 1 gets mapped back to 0. 0 gets mapped to minus 1 gets mapped to 0, 0 to minus 1, and so forth. It just bounces back and forth between 0 and minus 1. We call this a periodic orbit because it just keeps repeating. 0, minus 1, 0, and so forth. It's a periodic orbit, and the period is 2 because there's exactly 2 elements in that orbit. And such a point clearly needs to belong to the filled-in Julia set because the orbit never runs away to infinity. It stays between 0 and negative 1. Let's look at another point z. Let's look at the point z equals 1. 1 gets mapped under f to 1 squared, which is 1 minus 1, that's 0. 0 gets mapped to negative 1. As we found before, negative 1 gets mapped to 0, 0 to negative 1, negative 1 to 0, 0 to negative 1. So 1 itself isn't a periodic orbit because the orbit never returns to 1. It is called a pre-periodic orbit. Here's a picture of what happens. There's 1, and it's mapped under f to 0, and 0 is mapped under f to -1, and -1 is mapped back to 0. 0 is to -1, -1 to 0. So this is a graphical picture. Here's the periodic orbit, and 1 enters that periodic orbit. So it's pre-periodic, and then it's part of that periodic orbit later. Clearly, 1 also belongs to the field in Julia set because this orbit stays very bounded, never goes off to infinity. Look at another example. Z equals 1 plus square root of 5 over 2. What is f of z? F of z is z squared, so 1 plus square root of 5 over 2 quantities squared minus 1. Let's multiply through. 1 plus square root of 5 quantities squared is 1 plus 2 times square root of 5 plus square root of 5 squared, which is 5. We square the denominator as well, which gives us this 4. And then we need to subtract 1. Let's find the common denominator, which is 4. So we subtract 4 in the numerator if we make this 1 into a 4 divided by 4. And we are left with 2 plus 2 square root of 5 over 4. That simplifies to 1 plus square root of 5 over 2, but that's the z we started with. So we found a point z, namely 1 plus root 5 over 2, that satisfies that f of z equals z. Such a point is called a fixed point of f, because f takes that point and maps it to itself. It's fixed under f. Has to belong to the field in Julia set as well, because the orbit stays very bounded and never leaves the point z. So far, everything we've tried belongs to the field in Julia set. Let's find some more orbits. How about z equals -2? -2 squared is 4 minus 1, that's 3. 3 squared is 9, minus 1 is 8. 8 squared is 64, minus 1 is 63, and so forth. It looks like this is an orbit that has a chance to go off to infinity. So we think that -2 belongs to a of infinity, because that just keeps getting bigger and bigger and bigger. How about z equals I? I squared is -1, minus 1 is -2. -2 squared is 4, minus 1 is 3. And we notice, wow, we are in the same picture as we were in before. We started with I instead of starting with -2, but after that, we ran into the same orbit that we were in before. So if -2 belongs to a of infinity, so does I. But how do we know for sure that the orbit of -2 goes off to infinity? It seems pretty clear, but it would be nice to know for sure. One can actually show that if x is on the real axis and smaller than -1 plus root 5 over 2, or bigger than 1 plus root 5 over 2, then it belongs to a of infinity. So that was our fixed point. 1 plus root 5 over 2, that was the point that was fixed under f, and here it's negative, -1 plus root 5 over 2. That is not a fixed point of f, but it's the negative and is mapped onto the same point as 1 plus root 5 over 2, because when you square this function and then subtract 1, you're also mapped to this point. Is mapped here, and this point is mapped to itself. If you are either out here or back here, all those points go off to infinity under iteration. More generally, if z is in C, whose absolute value is greater than 1 plus root 5 over 2, even that belongs to a of infinity. So if you draw a circle here through these 2 points centered at the origin, then anything outside of that circle belongs to a of infinity. Even more generally, if z is a point in the complex plane such that one of its iterates has absolute value greater than that circle radius, 1 plus root 5 over 2, for some n, then that z itself belongs to a of infinity. And a similar condition holds for general quadratic polynomials of the form z squared plus c, not just for the one z squared minus 1. The theorem is as follows. Suppose f of z is z squared plus c, and we calculate a radius r, which is calculated similarly to the previous radius up here. 1 plus square root of 1 plus 4 times the absolute value of c divided by 2. We had c equal to -1. The absolute value of c is 1, so that gives you a root 5 here. So 1 plus root 5 over 2 is exactly the radius that we obtained that way. Suppose that c0 is a point in C. If for some n, the nth iterate of c0 has absolute value greater than this r, then the iterates go off to infinity as n goes to infinity. In other words, z0 belongs to a of infinity and not to k of f. Well, that sounds like a condition a computer could check. And indeed it can. So here's an algorithm to find the filled-in Julia set. Given a value of c, calculate that radius. 1 plus square root of 1 plus 4 times absolute value of c over 2. Choose a window of z values that you want to check. So find some a and some b and a c and a d. And you want to check a window like this of z values, and you want to check which of these z values belong to the filled-in Julia set. Typically, you would want something rectangular that is centered around the origin, and typically you would want that ball of radius r to be part of that because the filled-in Julia set is typically contained in there. So you want the window bigger than that, unless you wanted to zoom into your Julia set. But typically you want that window to be at least as large as this radius, and probably you would want to choose something symmetric around that radius, but it's really your choice. The computer can't really check all iterates fn of 0. So at some point, it'll have to stop. So pick a largest number, maximum number of iterations. You can start with 100, later on go up to 1,000. It depends on how fast your computer is. You can go up to 10,000 even later on. So choose a maximum number of iterations up to which you want to check. The larger this number is, the more accurate your picture will get, but the slower the calculation will be. So start with something small while you're still developing your program. For each pixel on your screen that you'd like to color, choose a point Z in your window. So you need to find a correspondence between your screen and the window you chose for your Julia set, where you had chosen that probably large enough to contain that ball of radius r. So for each point on your screen, you need to find the corresponding point Z in your window. So your screen consists of pixels, and for each pixel you need to decide how does that correspond to points in your window, something like this. That's just a linear mapping, that's not very hard. Once you have found the coordinates of your point Z in your window, calculate its iterates. Find f of z, f of f of z, f of f of f of z, and so forth. If one of these iterates satisfies that its absolute value is greater than r, then you know this point belongs to a of infinity and not to the filled-in Julia set, so color it white. If you reach the maximum number of iterations, max iter, without having left this ball of radius r, there's a really good chance that this point Z belongs to the filled-in Julia set. It's not entirely clear, and so the larger you choose max iter, the more certain you will be that this point belongs to the filled-in Julia set. So color this pixel black. That corresponds to that point. This gives you an image of the filled-in Julia set. Let's look at some examples. Here you can see the filled-in Julia set for z squared minus 1. That's the function we were looking at earlier. Here's the filled-in Julia set of z squared plus 1/4. So c is equal to 1/4. It looks quite different from the previous filled-in Julia set. Here's yet another one. The one of z squared plus I. It looks quite different yet again. And here you can see the Julia set of z squared plus 1. It's a bunch of disconnected little pieces all over the place. The pictures we have produced so far of the filled and Julia set, they're black and white. You've probably seen more colorful pictures. So if you wanted to produce a more colorful picture, you need to choose colors C0, C1, C2, up to C, however many iterations you're allowing your computer to go through. And these are all colors in which you're going to color A of infinity, those points that escape to infinity. And then you need to pick an additional color for the filled and Julia set. Typically, that additional color is black, but you can pick whatever you want to pick. Now, if z is greater than r, then you know right out from the start that that point belongs to A of infinity, so color it in the color C0, the first color you chose. Otherwise, find its iterate. If the iterate is greater than r in absolute value, color the corresponding pixel in color C1. If it's not bigger than r, but its iterate is bigger than r, color the corresponding pixel in color C2, and so forth. So you are coloring pixels depending on how long it takes the corresponding point z to escape that circle of radius r. The longer it takes, the closer your color gets to the color from max iteration. Otherwise, if all of your fn of z's stay within the ball of radius r, color the corresponding pixel in the chosen color for the filled and Julia set. This gives you a more colorful picture. The larger this constant max iter is, again, the more detail you can see, but the longer the calculation will take. If you zoom into the Julia set, so if you choose small windows, a higher precision is required to avoid round-off errors. Let's look at some examples. Here are some colorful examples of Julia sets, and you can see their different natures. Here's one where you have a lot of black filled in, and here you can barely see the black parts. Here again, there's only specks of black and lots of colorful things going on. And here as well, the Julia set is very scattered throughout this picture. And here the Julia set has these round features, and here it consists of specks. So we notice the following in all the pictures we looked at. The Julia set is either in one piece or totally dusty. That leads us to the following definition. We say the Mandelbrot set is the set of all those parameters C for which the corresponding Julia set is connected, so in one piece. That a parameter C belongs to the Mandelbrot set if the Julia set of f of z equals z squared plus c is connected. In other words, the Mandelbrot set is a subset of parameter space, the subset of C values. Whereas Julia sets are always sets of Z values. They're both contained in the complex plane, so this can get a little confusing. But the Mandelbrot set, you should think about that as a set of parameter values. Whereas the Julia set, you fix a parameter value, C, and then look at Z values and find out which of those Z's remain bounded under iteration, which ones go off to infinity, and where's the boundary in between. Let's look at some examples. 0 belongs to the Mandelbrot set because we calculated its Julia set. The Julia set for the function z squared, which is the case when c is equal to 0, was the circle of radius 1. A circle is a very connected piece. It's just in one piece. And so 0 belongs to the Mandelbrot set. When c is equal to -2, we calculated its Julia set last class. We found that Julia set of z squared minus 2 is the interval from -2 to 2. That's again a connected piece, and so -2 does belong to the Mandelbrot set. 1/4 seems to belong to the Mandelbrot set as well, according to the picture that we saw. Here's the picture again of the Julia set of z squared plus 1/4. It's also called the Cauliflower set. It looks like it's in one piece, the boundary is in one piece, and therefore 1/4 belongs to the Mandelbrot set. 1, on the other hand, does not belong to the Mandelbrot set according to the picture that we found. This picture of the Julia set of f of z equals z squared plus 1 looks like it's completely, totally dusty and disconnected. You see all these little specks all over the place, but there's clearly huge gaps in between. So this set is not connected, and therefore the parameter 1 does not belong to the Mandelbrot set. Then how do you determine whether for a given C, the Julia set of z squared plus c is connected? Is there a way we can have a computer perform this task? That's what we're going to study in the next lecture.